Well, let's look at quadratic denominators, and this is important because remember we saw that everything can be reduced down to linear or quadratic factors, and the linears are going to be pretty straightforward because it's always going to be a log. Quadratics, how do we deal with them? We could have something like this, where we could end up with a difference of two squares. So you always do it on any quadratic, complete the square, you get difference of two squares. Yes, we could do that via partial fractions, but if we remember the pattern, it's a lot easier. So 1 on 2a, they've both got 1 on 2a at the front, they're both natural log, and you just see this difference fraction. And there is a way that I use to remember it. I have a look at what I'm integrating, and I look for where the x is, and that's how I'll either start or finish the integral. So if you look at the first one, it finishes with the x. More to the point, it finishes with minus x squared. Therefore, this integral must finish with the minus x. And when I say finish, I'm thinking, well, I'll write the numerator, then I'll write the denominator. So I finish with the a minus x. Whereas this one, it starts with x minus. Therefore, I will start it with x minus. Yes, it's just how my mind works. That's how I remember that one. The other possibility, of course, is the sum of two squares, and that's our inverse tan function. But then there are other things that could happen. Maybe we've got the square root on the bottom, and we know the square root of a squared minus x squared, that's inverse sine. But what about when I flip it the other way around? If it's x squared minus a squared, it actually turns out to be this, the log of x plus the square root of x squared minus a squared. And then the third thing we could have is when it's the sum of two squares, and very nicely that one turns out to be very similar to the other one. And you'll notice they're both log of x plus, and then it's just whatever the square root sign was. Well, the first thing to do is to complete the square, so I can write it as either the difference of two squares or the sum of two squares, and then I'll know what it's going to be. And this one here, sum of two squares, I know it's going to be inverse tan. So we've got 5 times 1 on root 5, inverse tan, x plus 2 on root 5. Then I get something like this. And when I see something like this, where it's not a constant number on the top, I just immediately go, right, I'm going to create two integrals here. And there's my two integrals. First integral becomes du on root u. Du on root u. That's the one thing, because I know that's 2 root u. I just want to create it. So what I do is I just write whatever that derivative is on the top of the fraction. I just write it there. So I've got du on root u. I know how to do that. Now obviously I can't change the question, so I need to balance it out. Don't worry about the constant. The constant's irrelevant. I look at the x value. I go, I've got 2x, I want 3x. Therefore, I need to multiply by 3 on 2. So now I work out the constant that has to go on the other one, because now my constant is 3 on 2 times negative 4, which is negative 6. But I want it to be positive 2. So 8 goes on the other one. I've now got two integrals to deal with. The first one, as I say, is just du on root u. And if you didn't spot it, yeah, okay, we could do it via substitution, and there we go. The second one, I now go complete the square, and I see what form it's in. And this one's the square root of x squared minus a squared. What's that one? That's the log one. So log of x, well in this case x minus 2, plus whatever that square root was, I'll go back to the original one, x squared minus 4x plus 1. Oh, I haven't substituted back in for my 2 root u there. Let's do that. So substitute in the 2 root u, and we get 3 root x squared minus 4x plus 1. Bang. Something like this then. You see what? Quadratic denominator? Yeah, it is. What we do here is, instead of rationalising the denominator, let's rationalise the numerator. And I end up with one of these questions again. Okay, I know I've got two integrals. There we go. Create the derivative. The derivative is minus 2x minus 1. Okay, let's just look at the x values. In order to balance that out, I need minus a half. Minus a half times minus 1 is a half. I want 3. So I've got to add 2.5. 5 on 2. For some reason I put the 5 in there, and why wouldn't I just put 5 on 2 out the front? Doesn't matter. Got to complete the square on the second one. I've got du on root u on the first one. So we get minus root 6 minus x squared, and this one is in the form of an inverse sine. So those missing standard integrals, again, how my mind works. Okay, I've got dx on a squared minus x squared. That integrate finishes with the x, so my answer finishes with the a minus x. If I've got that one, it begins with the x, so this one begins with the x minus a. Let's play.